The next part of this video is going to talk about a theorem that we can use that's related to these ideas of maximums called Rolle's theorem, and it can be used to apply, it can be used as an application to solve different kinds of questions that we might have about functions. And so first we'll look at the theorem and talk a little bit about why it's true, kind of go through a little brief proof of it, and then we'll actually look at a specific example. So we are going to assume that f of x is continuous, so this is similar to the extreme value theorem. We have to have a continuous function on a closed interval, so from a to b, and it's also differentiable on that interval. If our f of a is equal to f of b, then we're going to get that there exists a c between a and b such that the derivative is equal to 0. So I want to draw a couple of pictures of why this is true so you can kind of understand where it's coming from. And there are really sort of two cases. So case one would be the situation where we're trying to find a c where the derivative is 0. Well, we know that the function's continuous on a closed interval, so by the extreme value theorem, we know if we have this function from a to b, that it has to have an absolute maximum or minimum on that interval, and I guess minimum and maximum. And let's say the first case is, suppose that the max occurs in between a and b. Right, so we know it has to exist. We're using the extreme value theorem. So the extreme value theorem guarantees us that this maximum will be there. And let's just assume in case one that it's actually in between. Well, if it's in between a and b, then that means that it has to be a space, that c where that max occurs. F prime of c will have to equal 0 in that case. So if the maximum occurs between a and b, then we know for sure there has to be a place where the derivative is 0, where that maximum occurs. If that's not the case, then we know the maximum has to occur on the endpoints, right? So if the maximum occurs at the endpoints, we can keep that in mind. So here's the max occurs at the endpoint. But the key thing to remember in our assumption is that f of a is equal to f of b. So if we were drawing this picture, here's a, here's b, that is the maximum, right? So we can't go above it, we can't go below it. So our function looks like this, and so certainly for any c in this interval, f prime of c has to equal 0. So those are kind of your two cases, is you have sort of f of a equaling f of b. You can have your max occur somewhere in the middle, or your max can be at the endpoints, but because the endpoints have to be equal in the assumption of this theorem, then you would get that the function has to be a straight line, and if it's a straight line, the derivative has to be 0. So in either case, you're guaranteed that there's going to be at least one number where the derivative is 0. And that's the idea of Rolle's theorem, and we're going to use that to prove something that doesn't look like it has anything to do with maximums, but this theorem can be used to help us decide that. So this example is to use Rolle's theorem to prove that f of x equals x to the third over 6 plus x squared over 2 plus x plus 1 has at most one real root. So that's what we're going to try to do. And the proof technique for this, so we're using actual kind of proof, and it's one of our sort of first proofs that we're going to do, is using an idea known as contradiction. So we want to show it has at most one real root. And that's a really hard thing to do. So what we'll do instead is suppose that f has at least 2 roots. So we'll suppose sort of the opposite. And we'll hope that at some point we'll call those roots a and b. we'll hope that at some point that causes a problem for us, and so we know that if that causes a problem, then it can't have at least 2, it must have at most 1. So that's kind of the idea, is we'll assume the thing that we don't want to show, we'll hopefully run into a problem known as a contradiction, and then be able to say, well, then that must not have been true. The thing that must be true is the opposite of that, which in this case would be that it has at most 1. So the opposite of at least 2, right, is having at most 1. So let's say, suppose it has at least 2, let's call 2 of those things A and B. Then if they are roots, that means that a root, remember, is something if you plug it in, you get 0. So that would be true for both f of A and f of B. But then, since f is continuous and differentiable by Rolle's theorem, we know f prime of c has to equal 0 for some c in the interval A to B. So we know that at some point the derivative is going to have to be 0. Since these two things are both equal to 0, that means f of A and f of B are equal. That's the assumption of Rolle's theorem. We have a continuous differentiable function. So the conclusion of Rolle's theorem is that the derivative has to be 0 at some point, because we have two endpoints that are equal. So at some point there has to be a c in that interval where the derivative is 0. But if we take the derivative, f prime of x, we can take that derivative probably pretty easily. We'd get 1/2 x squared plus x plus 1. And if you think about plugging numbers into this, these are always going to be numbers that are going to be greater than or equal to 1. Right? Because this value here is always going to be at least 0, and certainly will never be negative, because you're going to take a number, even if you plug in a negative number, you're going to square it first and then add x to that. So I don't think you're ever going to get below 0. So this number is always bigger than 0. You're adding 1 to it. So this whole derivative, so our derivative is always bigger than or equal to 1, because this piece has to be greater than 0. This piece right here is definitely greater than 0. If we add 1, that whole expression will always be bigger than or equal to 1. So f prime of c cannot equal 0. But if you noticed, we have f prime of c has to equal 0, and f of prime of c cannot equal 0. And that means that we have what is known as a contradiction. So on our last line, which I'll have to put on the next page, we'll say this is a contradiction, and so thus f of x can have at most 1 real root. And we have finished our proof, and so we can put these little nice lines there that say we're done. So the ideas that we started with, if we go back and look, we started with supposing the opposite of what we really wanted to show. We wanted at most 1. So let's suppose the opposite. Let's say we have at least 2. We named those roots A and B. Being a root of an equation means that if you plug it in, you get 0. And that meant that those two things were equal. And if you remember Rolle's theorem, as long as our function was continuous and we could take the derivative and the two endpoints were equal, that means at some point the derivative has to be 0, which is what we got here. So then we went ahead and took the derivative to see if that actually was valid. And when we take the derivative, we get that the derivative has to be bigger than or equal to 1, always. There's no value of x that's going to make it less than 1. So for sure then, that means that f prime of c cannot equal 0 for any value. Right? It will never be 0. So if the derivative has to be 0 for some c, and it can never be 0 for some c, that's a problem. So that led us to our contradiction. And so whatever we originally assumed had to be incorrect, and so we must have that f of x can have at most 1 real root.